All right, welcome back to the weekly fractional calculus seminar. Today's speaker is Professor Ravshan Ashurov, currently head of laboratory at the Institute of Mathematics of the Academy of Science of Uzbekistan. He studied at Moscow State University, receiving his PhD from there in 1982 and a Doctor of Science also from there in 1992. He has worked as a scientific researcher or visiting scientist at a number of institutions, including Birmingham University in England, Vanderbilt University in the US, and the ICTP in Trieste, Italy. He has published more than 100 scientific papers, as well as several books and monographs in English, Russian, and Uzbek. His research interests include fractional differential equations of ordinary and partial type, spectral theory of differential and pseudo-differential operators, harmonic analysis, and wavelet transforms. And today he is going to be speaking to us about inverse problems of determining the order of fractional derivatives in partial differential equations. Please, the floor is yours.
Okay. First of all, I would like to thank organizers of this seminar for giving me opportunity to talk today. It really was a very good idea to start this seminar. So, okay, this is the title of my talk. And, oh my God. Oh, yes. So today we will talk about a relatively new inverse problem, that is the inverse problem of determining the order of fractional differential equations. And in the last 10, 15 years, this type of inverse problem has been actively studied by many authors, and a number of interesting results have been obtained. There is a survey paper which is published in 2019. It's well-known in well-known handbook of fractional calculus by Li, Liu, and Yamamoto. So we'll give a brief overview of most interesting works in this area and propose a new formulation of this problem and show methods for solving it. Okay, let us assume that we are giving some domain and dimensional domain omega, and in this domain there is some subdivision equation is going on, which is modeled by the following initial boundary value problem 1 to 3. Here, this is a derivative in the sense of Riemann-Liouville. This is Laplace operator. This is Neumann boundary condition, and this is initial condition. Here, this corresponding standard definitions. This is Laplace operator. This is fractional integral, and this is derivative in the sense of Riemann-Liouville. And we'll also use derivative in the sense of Caputa, which is defined by this formula. So we call this problem as a forward problem. It often happens that this parameter rho, we don't know exact value, but we know that it is exactly within 0, 1. It's very important to know this exact value for solving this problem and investigating properties of this solution of this boundary value problem. And unfortunately, there is no device for accurately measure of this parameter. And there is only one way to find this parameter. It is analytical way. That's why we come to inverse problem. So 2 words about how we came to this problem. In 2020, when pandemic began, Professor Umarov from University of New Haven, together with his colleague, Yang Kuang Cheng from University of California, began working on problem of creating mathematical model of the spread of coronavirus among the population. The goal was to predict how many people would become infected by coronavirus or recover. It turned out that the system of differential equation modeling this process is a system of nonlinear fractional differential equations. And data presented by Johns Hopkins University on COVID outbreaks in different countries shows that the order of fractional derivatives lies within interval 0, 1. To find exact value, Umarov proposed to search this parameter analytically, and we came to this inverse problem. Now, as I told, there are many papers published and some of them included in survey paper, which I noted above, and some of them published after this. Will not stop on each of these works, but I want to give some general remarks. First of all, in all public papers, authors consider only derivative in the sense of Caputa. And secondly, all authors consider the subdivision equation. So that means parameter rho within 0, 1. And only homogeneous equations were considered, and spectrum of elliptic path of equation was discrete. And the main thing that authors proved only uniqueness of the solution. Of course, we know that uniqueness is very important from application point of view. But it is good if we know that the solution of this inverse problem exists also. There is one paper by Yano here, I presented, it is published in 2016. The author proved here existence also. And next thing is that all authors use the following determination condition, number 4. Here, x0 is some point within domain omega. And authors to prove uniqueness, they use asymptotic behavior of Mehta-Lefler function. That means this T, capital T, must be large enough. And if we come back to pandemic case, we will have to wait a very long time before making any prediction. So we will give another formulation of this problem and method of this solution. In this formulation, previously unconsidered case can be recovered, and also we can prove existence of this unknown rho. Before doing this, let's recall formulation in which inverse problem was considered. We'll call it inverse problem 1. So this is 5, inverse problem, which is written in 5. So first 3 lines, this is forward problem, and the last line is our determination condition. If we want to prove uniqueness, of course, we can do that for arbitrary h, because to prove uniqueness, it's sufficient to consider this problem only in case of phi equal to 0 and h equal to 0. Of course, natural question arises, if we want to prove existence of this rho, can we do this for arbitrary given h? The answer is no. Why? Because x0 here is from domain omega, where we have equation, subdivision equation. That's why h must be trace of the solution of subdivision equation. This is number 1. And number 2, we know that all solutions of this equation is infinitely differentiable. Then this ht also must be infinitely differentiable. It turns out that this is not enough. We can see this theorem 7.2 from work 2, where author formulated existence. And this theorem formulated on more than one journal page. That is, it requires fulfillment of a large of conditions for data of problem. So thus, we can say that we cannot solve inverse, prove existence of the inverse problem for arbitrary given h. In this connection, in survey paper 1, it was formulated the following open problem. Is it possible to investigate inverse problem using the value of solution at a fixed time t0 as observation data? For our part, we would add that if we want to find only one number, rho, then it's better to indicate also one number. Okay, based on this, we propose the following overdetermination condition in the form of 6, where f capital is some functional and not necessarily linear. And this is solution of that equation, and therefore it depends on rho. So that means this function 6 here, we can define as f of rho, then condition 6 can be rewritten in the form of 7. Now, our task is to find such a functional F capital so that F of rho is strictly monotone. If we succeed in this, then equation this to find rho has unique solution if and only if D0 lies in this interval. It's obvious. If D0 is out of this interval, then you cannot find rho. Okay, now we will formulate new formulation of this inverse problem. We call it inverse problem 2. Again, first 3 lines, it is forward problem, and we add additional condition in the following way. Here we have V1. What is this V1? V1 is eigenfunction of this spectral problem. Here is this Neumann condition, boundary condition. And obviously, first eigenvalue here is 0. If you put here 0, then you can take as an eigenfunction constant. To make the norm of this constant 1, you can choose eigenfunction in this way. So as an additional condition, we take solution of this problem, forward problem, and put T0 and multiply scalarly by V1s. In this case, we have this integral. An additional condition is that this integral equals to D0. I should tell that for our reasoning, this lambda 1 equal 0 is very important. Actually, not first eigenvalue. It's sufficient sum of eigenvalue to be equal to 0. So if we go back to pandemic case, this condition means that we should know that the number of infected people in the country omega for fixed time, for example, today. And then we can solve this inverse problem. Now, recall this Mehta-Leffler function with 2 parameters has a form. Now, if this sufficiently smooth enough phi in the forward problem, then we can solve this forward problem by the Fourier method and get this solution. Here, phi g is Fourier coefficients of initial function. So now we want to find f. How to do that? We just multiply this sum by v1 scalarly, and then since the eigenfunction v1 orthogonal for all other eigenfunctions, then here we have only first term. And then if we know that lambda 1 is 0, then f rho is this function. Or using this value of this Mehta-Leffler function, you have very nice function 9. Now, for this function, it is easy to prove the following lemma. So if this is satisfied, then f is strictly monotone, and at 0, it is equal to 0. At 1, it's equal to phi1. We say this is strictly monotone, and it will be decreasing if phi1 is negative, and it will be increasing if phi1 is positive. So we wanted to solve this problem, and now we know that this is strictly monotone, and if D0 lies here, then we have unique solution. So therefore, we have the following solution for inverse problem 2. Let phi1 is not equal 0, then inverse problem has unique solution if and only if 11 satisfied. So we know that solution exists, and to solve this functional equation numerically, we can use any known methods, for example, Newton method. Okay, now this result is published in paper 3 with Umarov in 2020. And then in this inverse problem, we can also consider non-homogeneous subdivision equation. What kind of problem arises when we consider non-homogeneous equation? You see, above we proved that rho, this is unknown parameter, depends on initial function. But if you have right-hand side also, then this parameter would define it's also depends on right-hand side also. And the question is how it depends. The answer is given in this paper 4 with Faizi, co-author Faizi from National University. It was published in 2021. And again, in this inverse problem, we can consider fractional wave equation as well. And this corresponding result was published in paper 5 with Sitnik, Sergei Sitnik, he's professor from Russia. So here again, problem is that you have, when you consider wave equation, you have two initial conditions and right-hand side also. Just to show what kind of problem here arises, let's consider the case of when right-hand side equal to 0 and rho is in this interval. Then additional condition will have the following form. You see, now you have to prove that derivative of this function doesn't change sign. So to do this, you must compare derivatives of these both functions. It is quite complicated job. Okay, and now, inverse problem 2, we consider only Laplace operator with Neumann condition. Of course, we can consider arbitrary elliptic differential operator here, and with arbitrary boundary conditions. The only thing we need is this set of eigenfunctions must be complete in L2. And also, first eigenvalue should equal to 0. And I should note that this paper 5, we consider not even elliptic operator, but arbitrary positive self-adjoint abstract operator. Okay, but we have two disadvantages of this problem, inverse problem 2. First is restriction lambda 1 is equal to 0. And second, you see, we considered only Riemann-Liouville derivative. We cannot consider here in this inverse problem Caputo derivative. Why? Because if you have Caputo derivative, solution will have the following form. And if you find f of rho multiplied by v1, you get here this function using this lambda 1 equal to 0, you have v1. So that means this doesn't depend on rho. So this method, which we showed above, we cannot use for the Caputo derivative. Now we'll give another method in which this condition is removed, and also we can consider Caputo derivative as well. Okay, now let's consider inverse problem 3. Again, first 3 lines, it is a forward problem, and as an additional condition, we take this norm, fix T0, and take norm equal to D0. And here you see the T0 should be sufficiently big, T0. So actually this inverse solution of this inverse problem immediately follows from this lemma. Lemma 3 says that this function is monotonously decreasing with respect to rho when rho is separated from 0 and this T0 is sufficiently large. So once you have proved this lemma, then you have this result. The inverse problem has unique solution if and only if D0 satisfies this inequality. Now, we are left with the task of proving this lemma 3. So one thing we should note that theorem 4, which was just now formulated, it's proved in this paper with Alimov. Alimov is my supervisor, Professor Alimov from National University. This paper was published in 2022. And I want to say that theorem 4 gives positive answer to the open problem, which we noted above. Now, a few words about the proof of lemma 3. Okay, solution has this form. We fix T0. By Parseval's equality, this norm has this form. Now, these are positive numbers. And if we prove that this function here, which we denote by E lambda, right? This function is positive and strictly monotone, then this function will be also strictly monotone, and this solves the inverse problem 3. So now we want to prove that this function is positive and strictly monotone. This is proved in this lemma 5. So rho 0 is separated from 0, and T0, T capital 0 large enough, then this function is positive and monotonically decrease in rho for all T0 and lambda. So how to prove this lemma 5? We introduce this standard Hankel path when beta is in between 0p. This is definition. And if you choose beta within this interval, then in this book, the Ravshan, it proves the following equality, 13. So this function which we want to investigate has this form. Now, we choose for our convenience beta equal to this, and recall this function, and we show that derivative of this function is negative with respect to rho. You see, this is the most difficult place of the proof. You see, why? Because you see how this function depends on rho. Here you have rho, here you have rho, here you have rho, here, and everywhere here you have rho. But the important thing is that this domain of integration also depends on rho, you see, because beta is equal to this number. So, but still, we could manage to prove that derivative is negative for all rho and for sufficiently large T0. And positiveness of this, it's consequence of this equality, because once you have increasing function, and you know that at the end it is positive, then everywhere it is positive. So this way we prove lemma 5, and then sufficiently that is enough to prove to solve inverse problem. Now let's consider inverse problem with Caputo derivative. In this case, we have the following solution, and then capital F will have the following form, and the same for this function we have the following lemma, and this lemma proves inverse problem 3 with this Caputo derivative. This lemma says that this function here is positive and monotonically decreasing with respect to rho. This with Caputo derivative, this result was published in this paper in 2020. Okay, how to prove this lemma 6? Again, we take Hankel path. Here we choose beta equal to this, and using again in this Ravshan's book the following equality, and then take derivative and show that this derivative is negative. After proving this level, we have the solution of the inverse problem. We note one more paper which published recently, 2023. The authors of this paper proved that derivative of this function is negative, but for sufficiently small lambda. Lambda should be sufficiently small. And this is not enough for our consideration because lambda is here, lambda goes to infinity, and sufficiently small lambda is not enough for our reasoning. Okay, now, we have, this is some options of overdetermination conditions. So we have considered the following overdetermination condition, and now we will show that instead of this, we can consider many other options. Let A be Laplace operator with Dirichlet condition or Neumann, and let Vk and lambda k are corresponding eigenfunctions and eigenvalues. Consider continuous function and define the following operator. And let this domain of this operator belongs to domain of definition of operator R. In this case, we can take the following overdetermination condition with arbitrarily phi, capital phi. Because this is, in fact, this norm is equal to this, and these are positive numbers. And again, we should prove that this is positive and also strictly monotone. And in fact, this was proved in lemma 6. That's why we can take this overdetermination condition. And now we can choose this function. For example, if we choose like this, then we have this function, capital F equal to this. This is, in fact, full energy of the system. If we take, if we choose lambda, then we have this function as a f, capital F. And in our case, when we have norm of the function, we have chosen f phi lambda equal to 1. Now, we will show some equations for which we can apply our method, which we presented above. First of all, we will consider some operators with continuous spectrum. Let's AD is a positive elliptic differential operator with constant coefficients, and consider this operator in Rn. In that case, this spectrum of this operator is continuous from 0 to infinity, and we consider the following forward problem. This is differential equations with Caputo derivative. We can take here Riemann-Liouville also. This is initial condition, and this is we consider as boundary condition. And this initial boundary value problem considered in the paper 10, Zununov is from our institute, and this was published 2020. So in this paper, it's proved that this problem has unique solution in the following form. If phi, this initial condition from this Sobolev class. By the way, we should note that this condition is cannot be improved, because if you put here even equal, then in this Sobolev class, there are unbounded functions as well, but phi must be continuous. Okay, now for this forward problem, we consider the following overdetermination condition. We should note that when spectrum is continuous, the problem was how to find additional condition. So as an additional condition, we propose this Fourier transform of this function, and you know this Fourier transform. Oh my God! Sorry. Yes, Fourier transform of solution is just this function, right? So we put here this function. Now, what is C0? C0 is chosen in such a way that this Fourier transform of initial condition is not 0, and we put lambda 0 this number. So we have this. Now, to solve this inverse problem, we should show that this is strictly monotone. And this we have already shown. That's why for this problem, we have the following theorem. So the solution of inverse problem exists if and only if 17 is satisfied. Okay, now we consider Rayleigh-Stokes equation, and well, slightly change the previous method. We can prove inverse problem for this equation as well. So this 3 lines is called Rayleigh-Stokes problem. Here, this is just classical derivative. Gamma is positive number, and this is Riemann-Liouville fractional derivative, and alpha lies within in this interval 0, 1. Okay, as an additional condition, we take this one. So norm at T0. This forward problem plays an important role in describing the behavior of some non-Newtonian fluids. And in the derivation of this problem, can you see in these papers 11, 12? And in the last 10, 15 years, this problem has much attention due to its application, importance for applications. You can see some papers from 13, Mezhlikova. And now, you see, since this is important problem, Rayleigh-Stokes, we try to consider for this inverse problem, and we solve this inverse problem. So this, what is the problem here, even for forward problem? Problem is that you have both n classical equation derivative and Riemann-Liouville derivative. So very good solution of this problem was done by this paper, Mezhlikova and others. Solution has this form. Capital B has this form, and here B alpha has this form. And this additional condition is norm of this. It is you can calculate this norm as written here. And you see, previous case, we had, instead of B alpha, it's the Lefler function, and now we have different function. And we should show that derivative of this function with respect to alpha doesn't change sign. You see, it is very complicated function if you consider as a function of alpha. Here, B alpha has, you see, everywhere alpha, but still, it's possible to prove the following lemma. So derivative of this function with respect to alpha is negative if T0 is large enough. So once you have this lemma, you can prove this theorem 9. So it says that norm is strictly decreasing in alpha. So this theorem actually implies unique solvability of the inverse problem, but I think that this lemma has also independent interest, because it says that norm, L2 norm of solution of Rayleigh-Stock equation has a maximum value when alpha is close to 0 and minimum value when alpha close to 1. So now we will consider some mixed type equation. So let's consider this problem. Here you have a derivative in the sense of Caputa. Order is in between 0, 1. And if t is greater than, if t is positive. If t is negative, you have the order of derivative in between 1 and 2. And this is boundary conditions, this is initial condition, and this is so-called Boolean condition. This problem, we call it forward problem, was considered by Zhuzhansky and Karimov in these years, but n was equal to 1. And they investigated inverse problem on finding right-hand side. We put here 0, just we can also consider with right-hand side, but it will be technically more problem. So what we do is we want to find both derivative orders, alpha and beta. In this paper, we solve this problem in n-dimensional case, and solution has this form. When t positive this way, and when t is negative this way. It's here very important to note that this denominator is positive when you take t, capital T, big enough. Now, we put, once we have two unknowns, we put two numbers, two overdetermination conditions. F capital 1, F capital 2 equal to T1, T2, different times instance, T1 and this T2. You may ask, why here you take L2 norm, why you take here scalar product? In fact, we can take here also scalar L2 norm, here also scalar product. In all the cases, we can prove this uniqueness of the inverse solution of inverse problem. But as an example, we consider in this way. Okay, K0 is chosen such a way that this Fourier coefficient is not 0. So if we now find this function using the solution, explicit form of solution, then F capital 1 equal to this, and F capital 2 equal to this. Now, important, remember, this is like this. Important thing is that here in the second equation, this left-hand side doesn't depend on alpha. So what we do is we just prove that derivative of this is the most difficult place of the proof. We prove that this function, if you consider as a function beta, you see, it is quite complicated function, and derivative doesn't change sign. If derivative doesn't change sign, then from here we find beta, and putting beta here in first equation, we find, you know, this just we considered above that this is positive and also strictly monotone. That's why we have unique alpha here. In this way, we solve the inverse problem. And for our best knowledge, this is the first work where the inverse problem is investigated for equations of mixed type. Now, we will consider two inverse problems, which is related the problem under consideration. First, in paper 16, which is published 2020, authors consider the following problem. Here, simultaneously, they found two unknowns. Of course, U also and right-hand side and this other row. Here, this omega is unit disk in R2, and rho is in between this interval. And authors succeeded only in proof of uniqueness. They proved only uniqueness. Now, in this paper with Faizi from National University, we consider this problem in arbitrary n-dimensional domain and is arbitrary. And rho here was in this interval, we consider in arbitrary interval. And also we proved not only uniqueness, but existence as well. So just recall that they consider the following two overdetermination conditions. Instead of this, we consider the following two conditions. This is to find the order derivative, and this is to find right-hand side. And for this problem, we have the following result. So if T0 is large enough, and one of the Fourier coefficients of these functions is not zero, then the solution of inverse problems, that is U, F, and rho, exist and unique if and only if the following inequality is satisfied for D0. Now, we consider so-called two-parameter inverse problem. In 2013, Tatar-Ulusov considered the problem of finding two order of derivative. So in this equation, rho and sigma are unknown. They consider in this interval one-dimensional case. This is Laplace operator in one-dimensional case. And then rho is between 0 and 1, and sigma between this interval. Phi is infinitely differentiable. This condition is very difficult to check, that all Fourier coefficients must be positive, not non-negative. So the authors proved only uniqueness of this theorem with the following overdetermination condition. We should note that 0 is inside the interval where we have this equation. And Yamamoto in 2020, he considered the same problem in n-dimensional case with the following overdetermination condition, and he proved also only uniqueness. What we do is in this paper with Suleimanov, his master student in National University, we consider the same problem in n-dimensional case, and sigma is arbitrary, rho is separated from 0 and also separated from 1, and then two these overdetermination conditions. And we proved that these both unknowns can be found uniquely if and only if D0 satisfies this inequality and D1 satisfies this inequality. Now, just two words about the proof of this result. So what we have is, we have two equations, system of two equations, where unknown is sigma and rho. This T0 and this T1. So it is well known that solution of this system of equations will exist and unique if and only if this determinant is not zero for all rho and sigma. And we take these derivatives and show that if T0 in T1, which is in overdetermination conditions, are large enough, then this determinant is positive. So at the end, I want to like to note one recent paper by Arytushin. He is from Russia, this paper published in 2023. The author considered inverse problem with variable order. So the order of derivative depends on x. And with initial condition 0. Then he proved that if f, right-hand side, and its derivative satisfy certain conditions, and then rho exists, if the following condition, if P satisfies the following conditions. First, it is from Sobolev space and is positive and satisfies the following conditions. So this is just boundary condition, as was here in the equation, in the problem. And then this inequality. So from here, where G is this function, from these inequalities, we can see that T here sufficiently small. This is very interesting result. First of all, this rho is here depends on X. And secondly, they prove uniquely solvability of this problem when T is sufficiently small. You see, in all our works, in papers, we prove uniquely solvability when T capital is large enough. But here, he proved when T capital is small enough. So this is unpublished paper, unpublished work. Motivated from this work, we with Suleymanov, his master student at at National University, we proved the following two theorems. So this function is monotonically decreasing for all rho if T is sufficiently small. And the same for this function. So this we need to consider equations with Caputo derivative, and this statement we need when we consider Riemann-Liouville derivatives. So using these two statements, this paper will appear very soon in Archive. Using these two statements, we can prove all the above theorems, not for sufficiently large T0, but for sufficiently small T0 as well. So actually, this was what I was planning to tell today. And thank you for your attention. If any questions, you're welcome.
Thank you very much for the talk. Does anyone have any questions, comments? You can unmute yourself and ask directly.
Yes, I have a question.
Yes,
so thank you for a nice presentation. I was wondering whether you see some possibility to find the order of the fractional derivative if you have time-dependent operator. So now all operators were time-independent, if I'm not wrong. And the approach was building on the solutions. Do you have an idea how to approach the problem if you don't have this information?
Yes, Carol, thank you very much. It's a very interesting question. You see, the method we use everywhere in these works is the Fourier method. And the equations which we were talking about, we cannot use Fourier method. That's why you should use some other method, but we don't know yet what to do. But you see, the last paper which I noted here by Artushin, this is, you see, rho depends on, and in fact, in his equation, I put here Laplace operator, but in his equation, instead of Laplace operator, he considered differential equation which depends on T also, you see. So that's why maybe using this method, we can succeed in doing this, but still we didn't do that. Thank you for your question.
Okay, thank you.
Any other questions, comments?
Arran, my question is just a continuation of a question of Carol. As Carol mentioned, there might be the time-dependent coefficient, let's say the t in some power multiplied to fractional derivative. In that case, as a solution, you will get the Kilbasego function instead of Mittag-Leffler. So maybe it is possible to prove that monotonic increasing all these, just to consider this finding of unknown fractional order, just to study the properties of this Kilbasego function. Do you have some attempts on this? So?
Yeah, thank you very much for interesting question. Yes, we thought about that. Yeah, with some t here in power, and even right-hand side also in some way depends on t. Then we have solutions. Yes, with instead of Mittag-Leffler someone. You see, even in case of Mittag-Leffler function, to take derivative by the parameter, it is quite difficult thing, and then we should take estimates. But for that, we didn't do yet. Yes, thank you. This is maybe for future work. Yeah, thank you.
I had also another comment or question. This concept of determining the unknown fractional order is very interesting, and of course, something you can only do with fractional problems, not with integer order.
Yeah, yeah.
For operators where you have more than one parameter, like for example, in Prabhakar fractional calculus, you have an operator with 4 parameters and a semigroup property in 2 of them. Do you think it would be possible to extend this work to solve for more than one parameter?
Yeah, we have considered some problems, as I mentioned above, with 2 or 3 parameters. Yes, but the equation which you are talking about now, we didn't consider, but maybe we try. Yes, thank you for question, Arran.
Thank you. Any other questions, comments? All right. If not, then again, thank you very much for the talk. You've enjoyed listening to it. I will stop the recording here.